I'll explain. Okay, so today is about talking about how we actually use our titration formula that's given to us in Table T. Okay, we had one piece of homework, and I want to review this right now. It was number 12. And here is the classic example in here. They're going to give you three pieces of variable, three pieces of data. Okay, look, I have a molarity of something with an H in front. That screams acid. Then I have a molarity of my something in front that has a hydroxide. That screams base. And then I have a volume. So the point in these neutralization problems, specifically this type of problem is called a titration problem, is we want to figure out something. Now in this problem, we want to see how much of the acid is needed, what volume, how much of it, of this concentration, is needed to completely neutralize this amount of hydroxides. Now, what you're really doing, as we talked about yesterday, is you're comparing moles of H plus to OH minus. So my friends in chemistry, what you're doing is you're trying to say all of the H pluses from the acid, how much volume of that concentration do I need to completely neutralize? Neutralization means that all of the positive protons plus the hydroxides make water. That's what we're doing here. So in this problem, you have to identify the fact that I have an acid and base, and they're trying to figure how much acid, how much base do I need? What's the concentration do I need? What's the volume I need to neutralize? When I spilled the acid on my pants in the lab, how much base would I needed to neutralize? When I drank the acid, how much base did I have to drink to protect my throat? So we do this with this formula that compares moles of what? Moles of H pluses to moles of hydroxides. And it works like this. Molarity times the volume of an acid, so sometimes you'll see the little A here, equals the molarity times the volume of the base. Okay, we talked about this. So we have the molarity of the acid to be 1.5 molar. The volume is what we don't know. And the molarity of the base is also 1.5. So you may think it's the same amount, but maybe it's not. The molarity is not 1.5. The molarity is 4.0. Okay, it wouldn't have mattered, but I want to keep it under the same contents here. 1.5. And I just did the same number. 4.0, my bad. So 4.0. And the volume, I can do this, 1.5 liter. Okay, so how much volume do I need? Now molarity is moles over liters, this is liters, so when you multiply like we showed yesterday, what you're really doing is comparing the moles of this and moles of that. That's how it works. So let's do the math. 4 times 1.5 is what? 6. So I get 6 equals 1.5x. Divide by 1.5, what do I have? And we get 4. What do we get? 6 divided by 1.5? 4. Now, is that any surprise to anybody? If I have the same volume, if I have 1.5 molar and this is 1.5 molar, I'm sorry, if this is 1.5 molar, okay, and you can see 1.5, what number equals 4 times 1.5? It would be 1.5. But let's think about this for a second. Okay, so this is 4 liters. Or is this milliliters? Yeah, liters. So it took 4 liters of this acid that's 1.5 molar to completely neutralize 1.5 liters. Okay? Why did it take so much volume? Think with me. Why did it take so much? 4 liters to neutralize 1.5. What was the difference? This acid is so much concentrated, so much more concentrated. There's more H pluses. In this case, so much, this is base. So many more hydroxides here than H pluses, so needed a lot more. Is this the answer? Is this the final answer? No. Because look at the acid. You have to watch this. There's 2 H's here. So when I'm solving for this acid is really twice as concentrated as I suspected. So don't I need half as much? If this is twice as concentrated, don't I need half as much? So the answer would be 2 liters. What did I teach you yesterday? If you don't like to think like that, this one has 2, right? 2 H's. Put the 2 on this side. And if you put the 2 on this side, this 2, when you solve for it, will be down here. So this answer, my friends, is not 4 liters, it's 2 liters. Okay? It's the only thing you have to do. So if you do an MV equals MV problem, and that's where the titration problem, neutralization is, you've got to watch your acid and bases. There's 2 of these per 1 hydroxide. Most of them are just 1-to-1. Just solve for the unknown. So this was 4 liters, it was 1-to-1, but this is twice the number of H's than expected. And so we're trying to neutralize this base, and I found out exactly how much it would be for just 1 H. If I have twice the H's, I need half as much. If you don't like that, put the number that it is over here and solve for it. Yes?
I don't get where you got the 4.
Well, I solved for it without thinking about this. When I solved for X, plugging these numbers in, I got 4. Then I look back at my acid and base, and so there's twice as many H's given off here than here. I was trying to find exactly how much volume I needed to neutralize this base, to match up all the hydroxides. Because this was given off twice the number of H's than I expected, I need half as much. So 4 became 2. But if you don't like thinking that way, evaluate how many H's that come off your acid. This was 2. How many OH's come off your base? This was 1. Put that number on the same side and then solve for it. You get the same answer. Just be aware of that. 95% of your acid-base questions are 1-to-1. You don't have to do this, but you should have to check. It does pop up. Okay, we're going to use this formula to do this type of lab technique. Okay, this is called a titration. Now, basically a titration is when you use one chemical's information to get information of another. Okay? So this is what we're going to do in lab today. Okay? We're going to figure out what the concentration of this acid is. Everyone has acid. We have hydrochloric acid here in the beaker. Okay? In fact, the concentration, the molarity of this acid is what you're trying to find. Okay? So I'm trying to find the molarity of this acid. Now, what we're going to drop is a base. We're dropping NaOH. We're dropping a base. Okay, I'm not sure if I've ever dropped any base, but it's not, today we are. Okay? So I'm dropping hydroxide ions. Okay, because we know that this is going to break apart into Na+, which is going to spectate, and OH-. Okay, this dissociates, of course, into H+. So we've got H+ in here. Now, what we're going to do is keep adding the base until we reach the neutralization point, where the moles of the H+ equal the moles of the hydroxides. That's what we're going to do. So we're going to keep adding base until it equals. The question is, how do we know when they're equal? We're going to add a chemical indicator, phenolphthalein, a few drops. Okay? Now phenolphthalein, as we've studied, likes to turn pink at about a pH of 8 or so. So I'm going to add a few drops of phenolphthalein. Okay? It's going to tell me that, I'm going to start stirring this. For those that don't know, this is just basically a metal bar with a plastic coating. And the box it's sitting under is a magnet that's moving. So it's a magnetic stir. Okay? Of course, it's going way too fast. Looks like it's all or none with this one. All right, good enough. Now, why are we adding the phenolphthalein? Well, what pH does the phenolphthalein turn pink? Around 8 to 9, right? So here's the deal. When you'll do this in AP, when you plot the pH change, what pH are we trying to get here when the hydroxides equal the H+? 7. So here's what the pH, if we were to plot pH, okay, with volume of base added, we would get this curve. It's very steep next to the equivalence point. This is going to be a pH of what? 7. It's very, very steep. That's why I burn my throat. If I'm off by a little bit, it flies up. Once the pH starts getting close to the equivalence point, that's when these guys equal each other. You get a 7, but it's very touchy. If I was off by a couple of drops, I could be off by 10,000 or 1,000 times the concentration. And you'll see this firsthand today. So think with me for a second. Phenolphthalein starts turning pink around 8 to 10 range up here. You say, Mr. Grodsky, we're going to be off. We are, but because there's such a steep asymptote going up, the amount of volume that exists at this point to this point is what? Is it significant if that line is going straight up? The difference in volume that I'm adding a base, is there any difference from this point to this point if it's almost going straight up? And the answer is no. So we can use the indicator to estimate the pH of 7. Okay, and you're going to see this when you titrate. So what are we looking for? Well, we're looking for pink to persist for 30 seconds. So this is how you titrate. So here's what I'm going to do. I don't know the concentration of this, but I do know something. I do know that it's 40 milliliters. Okay, that's my volume. What's my M? I don't know. Equals the base. The molarity of the base, I do know. The molarity of the base is, in this case is, I think I might have used different values. It doesn't matter. Let's pretend it's 1 molar. Okay? So let's make the molarity 1 molar. And the volume. What am I solving for, guys? The titration. I'm going to figure out what volume, I'm going to measure how much volume is going to empty my burette that's going to get me to the equivalence point. So I'm solving for the volume needed to enter. So, did I add any in here? Looks like I did not. So let me add some base without spilling any. Making sure I have some base, yep. All right, so I'm going to add some base. Looks like it's starting to add already.
It fills up pretty quick.
It's a small tube. So now, I would measure the starting position of my burette. It starts at 0 because it's an emptying device. And here's what I'm going to do. I'm going to start dropping some base. Okay? Now, I want to figure out exactly how much. I mark my starting position of my burette, and then I keep adding base as I'm doing right now. I'm dropping some base right now. And anyone notice the color? It's clear, but look very carefully. Look very carefully. Do you see any color? Do you see a flash of color? Absolutely. The phenolphthalein, my friends in chemistry, is turning pink when it hits the hydroxides. What's happening to the hydroxides? What's happening to the hydroxides? Why is this pink staying there? Yeah, they're getting eaten up by the H pluses. I know when the H pluses have been neutralized completely, this is where I stop and I measure the volume, when that pink stays there for 30, slightly pink. So I'm going to keep adding base until this stays pink. Now if I keep going, you notice the pink is staying longer. If the pink is staying longer, I'm getting close. What am I after? I'm trying to find how much base volume I need to, when this stays pink, when it stays pink, I'm about the pH of 7. And then I can put this volume here, and I can do my math, and I can solve for the concentration of my acid. I'm trying to use this formula, but I got to figure out, is it staying longer? Yeah, so I'm going to open up a little more. Now you're going to go a little faster than this. So it's very touchy because the pH swings very fast. So I'm going to open this up a little bit. Maybe the wrong way. Oh. What's happening now? Anything? Is it staying pink? So I'm adding more, but I'm not there yet. So you're going to keep adding. You got to watch. Okay, it's staying pink. Not really. I got to add some more. Whoa. Is that pink persisting? It should start persisting longer. Need a lot more. Is the pink staying on longer? Yeah, as I get closer, the H pluses are getting used up, and that pink stays around longer. And it's telling me when to slow down when the pink stays there longer. I'm eating up the H pluses because I'm dropping the hydroxides and making water. Now that pink is staying around longer. So I should be slowing down and going slower because I don't want it to flash pink. Right now, I'm right here on the curve. I'm coming up. As soon as I take the turn, it's going to fly up real fast. Notice if I stop, it disappears. The pink shows because you see the hydroxide, but then it gets eaten up by the what? The acid. I'm getting close, party people. Whoa. It's got to stay for 30 seconds. It's a ghost. Not quite. I'm there, though. And you're looking for that perfect light pink. When you get light pink, oh, this looks blue on the screen. When you get light pink, is it purple? Yeah. Colorblind. Yeah. Colorblind's a dog, I guess. Am I getting close? Is it staying longer? I'm looking for slight pink. I'm about right here, guys. Is it staying for 30 seconds? It's alive! I think we're there. We'll be there. It's kind of weird how it's doing that. I'm not spinning this fast enough. Very close. One drop. Did you see one drop? Did you see what one drop did? Did you see how one drop flashed that? I must have. One more drop. One drop past it. Why did it change so bright? It flew up this asymptote. I'm at my endpoint. Measure the what? Final what? Well, you see how one drop made it flash? That's because of this asymptote here. So now I measure my volume, my start and final. I put that right here, whatever it is. Let's pretend it's 50 milliliters. Then what do? I solve for my x. That's what we're going to do. So in your lab today, you have in your beakers, write this down. Take out your data table. Okay, turn out your data table. You're going to do this right now. Go to the lab. Okay, it's lab 23. We're going to start collecting data. So we go to Dropbox, since I don't have it open. And we go to our lab. SkyDrive, Public. Let's go to labs. Regents labs. Go to 23. Okay.
That was so many different files.
Okay. Yeah, it was definitely crazy. Okay, here we go. So, here's what we're going to put. In each of your trials, you're doing 2 trials. Your standard solution is what we definitely know. So you're going to have a 0.1 molar solution of your base. Put it there. 0.1 molar. So you're going to have 0.1 molar. That's your standard base. Your base is NaOH. Why is it called a standard? Because that's what we're using to get the other. The acid we're using, guys, is HCl, but we don't know the concentration. We're going to do this. Volume of the acid, my friends in chemistry, we're going to start with 40 milliliters. So we're going to have 40 milliliters, 40.0 milliliters of the acid in the beaker. So look what we have. We know the what? We know the volume of my acid. We know the molarity of my base, which is 0.10 molar. What we have to find is how much volume of base you have to add till you get to that slight pink color. Notice one drop got you there. You just can't open it up and say, hey, I'm done. You have to go drop by drop as it persists. If you go too far, the pH will swing up here very quickly. From here to here can go in a drop or two. And that's the problem that I had. So once you have the molarity of the stance to be the same, volume of the acid is the same, start reading on burette. Move it to 0. Take your burette, look at the 0. There's a beaker that's a bigger beaker. Open it up to get to 0. Okay. Titrate to your little hearts away until you get this end point. Find the final reading of the burette. Find the total volume. Then calculate. I'm going to do this twice. Ready, set, go.